Hello students, let us start our new session of chapter number 11, Dual Nature of Radiation and Matter. Now let us understand the new concept, wave nature of matter. Matter is basically having some mass and which occupies some space. Here we need to understand that how this wave effect is available within the matter. Here we are having two different nature of radiation, wave and particle. So here dual nature of the light signal is available. Wave nature is defined that the wave nature of light signal shows the interference, diffraction and polarization. The best example is that any object is visible by our eye by the reflection of that light signal from the object, and that particular light signal can be captured by our eye lens. This is the example of wave picture. Here in photoelectric effect and the Compton effect, the energy and momentum will transfer which radiate and behaves as a bunch of particles are there, which defines as a photon, which is a particle, which is a quantum discrete effect. This, having the example, we can say that whatever the light is absorbed by the eye lens, now that data, this information is given by the rods and cones further of that retina, which requires a discrete nature of picture, that is a photon picture of light. Now here, these moving particles of matter should display wave-like properties under the certain conditions. This condition is given by the particular wavelength of that signal is given by French scientist de Broglie. So here, matter and energy both are having some symmetrical properties. Radiation actually shows the two different aspects, nature, wave and particle. So here de Broglie proposed that particular wavelength based on that momentum P equal to h by lambda. So lambda equal to h by P, and P, that is a momentum for the matter having a linear momentum, can be defined as a mv. Here v is the velocity or the speed of that particular particle, and m is the mass of that particle. This wavelength is known as the Broglie wavelength. This lambda is attributed of a wave, while this momentum p is attributed to the particle. So here the lambda and v both are there. V defines the velocity of the particle and lambda defines the wavelength of that particular wave. H is the Planck's constant. So for that particular photon, P equal to h by lambda, or we can say that hv by c. Here v is the frequency of that particular wave. If we rewrite that, that is h by p equal to c by lambda, this is nothing but wavelength. So this is a wavelength of the photon equal to the wavelength of electromagnetic radiation, by which the photon is a quantum energy and having a quantum momentum. If lambda is small, this lambda is smaller for a large particle and more for the small energetic particle having a higher velocity. If by having this equation, if we determine the wavelength of ball having the mass 0.12 kilogram, having the speed of 20 meter per second, so momentum in which m into v having 2.4 kilogram meter per second, let us substitute that momentum in the equation of lambda equal to h by p. So we able to get 2.76 into 10 raised to minus 13 meter. This wavelength is very much small, which we cannot measure even though by the... So here these microscopic objects in our daily life cannot show the wave-like particles having a larger mass. But in atomic and subatomic structure, this wave characteristic of particles can be significant, can be defined, and can be measured. For that, let us take electron as an example, having a mass m, charge E, which is accelerated between the potential difference V, having its kinetic energy K based on its work done in electrovolt. So here K equal to electrovolt E into V. Here having kinetic energy K equals to 1/2 mv square. So in terms of momentum, we are having 1/2 p square by m. So P equal to under root of 2mk, that is equal to under root 2m electrovolt E into V. So here, if we substitute the value of momentum P in the Broglie wavelength lambda, so lambda equal to h by P, that would be equal to h by under root of 2mk, that would be equal to 1 upon h upon under root of 2m E into V. So here, now substitute the value of h, Planck's constant, m, mass of electron, E, charge of electron. So we are having that equation lambda equal to 1.227 by under root V nanometer. Here V is the magnitude of the potential voltage. If we are giving 120 volt of the accelerating voltage, so we are having lambda equal to 0.112 nanometer. This wavelength is in the same order with spacing between the atomic planes in the crystal. Here these matter waves are associated with an electron, which can be verified by crystal diffraction using the X-ray diffraction analogy. De Broglie was awarded by the Nobel Prize in Physics for his discovery of wave nature of electrons. This matter, the matter which defines a wave picture, that also can be incorporated by Heisenberg's uncertainty principle. According to this uncertainty principle, it is not possible to measure both the position and momentum of an electron at the same time, because there is some uncertainty in the position defined as a delta x, and also uncertainty is available in momentum defined as a delta p. So here delta x into delta p equal to h dash defines h by 2 pi. Here if we are saying delta x would be 0 and h we want to make non-zero value, so for that delta p must be infinite, because if delta x is 0, make delta p would be infinite, then its a product value h dash it can be defined as a non-zero value. And if momentum uncertainty delta p is 0, then define delta x must be infinite. So both delta p and delta p are non-zero. For that again their product is in the order of h dash. So here by this particular uncertainty principle, let us define for the electron having the momentum p, and if we are taking that uncertainty of the momentum delta p equals to 0 by the Broglie relation having the wavelength lambda, and that wave is defined for the single wavelength which extends all over the space. But here electron is not localized in finite region of space, having the uncertainty delta extends to 0, which is consistent based on uncertainty principle. As delta p we are taking 0, then delta x should be infinite. So here this matter wave is associated with electron and it is not extended over all the space. So here this wave packet is there which is extending over some finite region instead of that single wavelength. So in this case delta x is not infinite, having some finite value in which a single electron or single wavelength is not extending all over the infinite space, but it is combining with wave packet. So what is wave packet? A wave packet having a finite extension which is not having a single wavelength, but that is built up of wavelengths spreading out by some central wavelength. As we can see in the diagram A, the center wavelength is maximum, then it will be reduced and spread over certain spectrum. This by that particular de Broglie relation, the momentum of electron will also spread by uncertainty delta P. And here this diagram A defines a wave packet radiation and diagram B defines extension of a single wavelength. Now let us focus the example. What is the de Broglie wavelength associated with an electron moving with a speed of 5.4 into 10 raised to 6 meter per second and a ball of mass 150 gram traveling at 30 meter per second. So here we need to determine this wavelength value. For that, mass of the object and velocity has been given. In first case, electron mass, that is 9.11 into 10 raised to minus 13 kilogram. Its speed is given 5.4 into 10 raised to 6. So momentum we are having m into v. Substitute the value of m into v. We are having momentum 4.92 into 10 raised to minus 24 kilogram meter per second. Now we are having the wavelength lambda equal to h by p. H is the Planck constant and p just we have derived. Substitute those values and we are having lambda equal to 0.135 nanometer. Now the same process, the same method we are going to follow for measuring the wavelength of ball having a mass 150 gram and speed v equal to 30 meter per second. So momentum p equal to m into v. Substitute the value of mass of ball and its speed, and we are having momentum 4.50 kilogram meter per second. Now substitute that momentum value in the Broglie wavelength lambda equal to h by p. So we are having wavelength 1.47 into 10 raised to minus 34 meter. So here we can say that the wavelength of electron is comparable with X-ray wavelength, but ball, that is about 10 raised to minus 19 times the size of the proton, and its wavelength cannot be measured practically experimentally. The next example is an electron, an alpha particle and a proton have the same kinetic energy. Which of these particles has the shortest de Broglie wavelength? So de Broglie wavelength is, for a particle we are having a lambda equal to h by p. Kinetic energy we are having k equal to p square by twice m. So lambda we have already calculated equal to h divided by under root of 2 mk. Here kinetic energy is constant, so we can say that wavelength is inversely proportional to the square root of their mass. Now mass of the proton, that is Ch11, that is 1836 times the electron, and alpha particle having 4 to He, that is 4 times that proton. So alpha particle has the shortest wavelength that we can define based on the mass of that particle. Next example is a particle is moving 3 times as fast as an electron. The ratio of that the Broglie wavelength of the particle to that of the electron is 1.813 into 10 raised to minus 4. Calculate the particle's mass and identify that particle. Here the wavelength equation we are having h by p, having a linear momentum h equals to p equal to mv. So h divided by m into v. So m we need to identify the mass, then mass m equal to h divided by lambda into v. So here for that electron, mass me equal to h divided by lambda e ve, and v divided by ve, that is here we are having 3, and lambda by lambda e we are having 1.813 into 10 raised to minus 4. So here in the comparison the ratio is given wavelength and mass. So that ratio we have defined with respect to electron. So now the mass of that, so here we can say that V by VE is 3 times as given in the example, and lambda by lambda E is given again in the given data example 1.813 into 10 raised to minus 4. So here the mass of the particle m equal to me into lambda e by lambda into ve by v. Substitute that, all the values are already given, and we can get the value m equal to 1.675 into 10 raised to minus 27 kilogram. So the particle having this mass, this can be proton or a neutron. Now next example is, what is the Broglie wavelength associated with an electron accelerated through a potential difference of 100 volts. So here according to this potential is given voltage equal to 100 volt. Then we are having the lambda equation equal to 1.227 divided by under root of V nanometer. Substitute that voltage value and we are having lambda equal to 0.123 nanometer. So this wavelength is associated with X-ray wavelength. Clear? Here we are going to end this session. With that we are going to end this chapter. Hope you understood thoroughly. Thank you.